in Remix quite a lot was we deployed our code to a Remix VM or a JavaScript virtual environment. We want to be able to do the exact same thing in Foundry in order to test and interact with our contracts. Foundry actually comes built in with a virtual environment in the shell. And if you run Anvil, you'll get an output that looks, and we pull this to the top, you'll get an output that looks something like this. Anvil, and we get some fake available account with some fake private keys. You'll also get a wallet mnemonic. The derivation path, which you can ignore, some details about the blockchain, and then this endpoint or RPC URL, which we're going to learn about soon. For now, if you want to close this, hit Control C or just delete your terminal to end running the Anvil blockchain. Now, moving forward, we're going to work with Anvil, but I do want to give you an intermediary step, and that's going to be with the Ganache ETH chain. And we'll have a link to this in the GitHub repo associated with this lesson. Now, and I want to give you a heads up. So Ganache is part of this suite of tools called the Truffle Suite toolset. And the Truffle Suite is actually being sunset. It's being deprecated. So in this video, I'm still going to be showing you some Ganache stuff. However, you do not need to download it. You do not need to do any of the Ganache stuff that I'm going to show you here. I'm going to go ahead and show you Ganache. However, pretty soon we're just going to do everything with Anvil anyways. So feel free to just watch, follow along, and then we'll actually replicate the exact same things using Anvil. So this is one of those times where you can just sit back and enjoy the ride. Don't do any of the Ganache stuff here. Just go ahead and watch me. But when we get to the Anvil section, we definitely want you to do the Anvil stuff. So great. Ganache is a one-click blockchain, and it gives us a user interface or an app for us to look at our transactions in an easier way. So if you go ahead and download it for your system, we can get started there. Now, a note for Windows users, if you're using WSL, the setup here is a little funky. We ran into some issues with it in our previous course, and we'll have some troubleshooting tips for those of you who are using Windows and WSL if you want to work with Ganache. Everything that we're going to be doing moving forward, though, does work with Anvil. Ganache just allows us to see transactions a little bit better than viewing all this stuff in the terminal. So if you're having a hard time with Ganache, don't worry. We can do everything that we're doing with Anvil, which should work for you, no problem. Once you have Ganache installed, when you open it up, it'll look something like this. And if we hit Quick Start for Ethereum, we'll actually create a brand new locally running blockchain with a nice little UI to view things. Same as Anvil and same as Remix, we get some addresses, We get each of them has balances. They come with some dummy private keys and dummy addresses and the likes. What's nice about this is that we can see the blocks, we can see different transactions, and if we're working with Truffle, we can see contracts. We're not going to work with Truffle though, but these are going to be very helpful for us to view stuff. Additionally, we're not going to use Ganache again in the future. So if you have trouble setting up with it, don't worry, just use Anvil. I'm going to use it to show you what's going on. Remember though, don't use these private keys on a public blockchain. It's for development purposes only, because everyone knows these private keys because they're dummy private keys. Now, in order for us to learn how to actually deploy to this blockchain, or how to deploy to Anvil if we're working with Anvil, we need to understand how even Remix was able to deploy to a public blockchain. When in Remix, when we switched to injected provider MetaMask, we know that MetaMask popped up. It asked us to add our password, and we went ahead and got connected. And if we looked in MetaMask, we saw our account is indeed connected to Sepolia. When we hit deploy, our MetaMask popped up again, and it was able to deploy our contract to a real test network. Well, how did it know where to send our transaction? How did it know where to send our contract? Well, let's go ahead and open up our MetaMask here. If we click the three little dots and hit expand view, we hit the little button now and we go to settings and we go to networks. You'll actually see in here that each one of these networks, Ethereum mainnet, Gorilli, Sepolia, Linea, or whatever you have, comes with a whole bunch of information. Let's go to ETH mainnet and check that out for a second. It has a name, an RPC URL, a chain ID, currency symbol, and block explorer. This RPC URL is the actual HTTPS endpoint that we actually send API calls to when we're sending transactions. So whenever you interact with MetaMask and you send a transaction or you deploy a contract, you're actually making an API call to whatever is in here. You'll see this is an Infura endpoint, and Infura is known as a node as a service project that allows you to send transactions to a blockchain node without having to run one yourself. If you wanted to send transactions to your own blockchain node, you would just swap this out with your own blockchain node address. We can't actually change the ones that come built into MetaMask, but we can add new networks, which is what we're going to do now. In here, if we scroll to the bottom, we can hit add network manually, and we can add information about our own custom network. So for us, we're going to make this new network called localhost or local chain or whatever you want to call it. For RPC URL, if you're working with Ganache, it's going to be this RPC server right here. If you're working with Anvil, at the bottom, we have this listening here. So what we would do is we would copy this, or we would copy this from Ganache and paste it in here. Just note that you always need the HTTP or HTTPS : // Most of our local applications aren't going to be HTTPS. They're just going to be HTTP. So if we're working with Ganache, let's go ahead and copy the Ganache endpoint, paste it in here like so. Every single blockchain gets their own chain ID. It's an easy way for us to know which blockchain that we're interacting with. Ganache has 1337, and Anvil doesn't say it, but it's 31337. So Anvil is 31337. Since I'm using the Ganache endpoint here, I'm going to type in 1337. If you're using Anvil, it would be 31337. But what's kind of nice is MetaMask can actually identify what you're using and identify the chain ID and basically tell you what chain ID to use. Just a note, it looks like the newer versions of Ganache are using a different RPC server and a different network ID. And make sure you're on this hard fork the merge here as well. Although in practice, I've found that even when you have 5777, it still is expecting 1377. So be sure to use the correct chain ID when you're working with this. Currency symbol, we're going to do ETH. And since this is a local blockchain, we don't actually have a block explorer. Etherscan has no way to connect to our own local blockchain. So we don't get a block explorer for this one. But if I go ahead and hit save now, it says network added successfully, and I can go ahead and switch to my localhost chain. Boom. And now we can see it in my list of networks. Of localhost, I've got no assets, no NFTs, and no activity. Now, if your local Anvil or Ganache chain isn't running after you've put it in your MetaMask, if you actually try to swap to your Anvil or to your localhost or to your Ganache, you'll just get this spinning wheel of death here, right? And eventually you'll get this little X that'll show up and you'll have to switch to a different network. So if you ever want to switch to one of these that isn't running, it won't work. You'll have to either run it or you can hit X here. And then in your MetaMask, you could just delete one of these right here. While we're not running our Ganache or our Anvil, we're just not going to have one of these selected. Great. And so this is where on both Anvil and Ganache, they have these available accounts and these private keys. Since I'm using Ganache, what I can do is I can select this show keys, copy this private key, and import it into my MetaMask. So I can go up, hit this little button. I can hit import account, paste my private key in here, and hit import. Now you'll see in my MetaMask, I have a couple different accounts. Account 3, the one I just imported, has 100 ETH. Why does it have 100 ETH? Well, because I'm using one of these dummy accounts from Ganache. And again, if you're using Anvil, they start with 1,000 ETH. This process that we just did to add our new Ganache local chain is also how we're going to add any EVM compatible chain on the planet. We'll just hit add network, and MetaMask actually comes built in with a lot of these. And for example, if we wanted to work with Arbitrum 1, we could just hit add, and it would add all this information in for us. Approve. Network added successfully. But if MetaMask doesn't have those built in, that's the process. Now, if we go back to settings, network, localhost, this endpoint is the most important thing you need to send a transaction to a blockchain. You need a connection to a node in order to send transactions to. If you wanted to send transactions to your own node, you would run something like Geth, which is an execution client, and then something maybe like Teku or Prism, which is a consensus client, and send transactions there. I'm not going to go over this right now, but I highly recommend that those of you who are curious, maybe you take some time and you try to run your own Ethereum node. I run many Ethereum nodes, and it's a lot of fun. That's kind of a weird thing to say. It's fun to run nodes. Whatever. It is fun to run nodes. Each one of these blockchains has different methods you could send to them to do things. If you're familiar with APIs and HTTP endpoints, and you go to this Ethereum JSON RPC specification site, you can actually see all the different methods that Ethereum blockchain nodes can make, and most EVM blockchain nodes can make. And when we actually sign and send transactions, it's these calls that we're actually making, like ETH sign transaction, send raw transaction, etc. We're actually not going to be going over interacting with these because Forge actually handles a lot of sending these transactions itself. If you want to learn how to send a raw transaction, making raw API calls to your own Ethereum node or an Ethereum node as a service like Infura or Alchemy, you would do that in a different programming language like Bash, Python, or JavaScript. All right, awesome. Now that we have our endpoint and our private key, we pretty much have everything that we need to deploy to our own local blockchain, be it Ganache or Anvil. Same as working with a real blockchain, we need an actual balance to spend gas to deploy our contract. Now, there's actually two ways that we're going to learn to deploy contracts. And the first way is actually with just working with the command line. If we're in our command line, if we're in our terminal here and we do forge -- help, we can actually see all the different commands that Forge comes built in with. The one we're going to be working with right now is this create command. And if you read it, it says it deploys a smart contract, which is perfect. That's exactly what we want to do. And if we're in our command here, let's hit clear and we do forge create -- help, we can see a ton of different options for deploying our contract. Click Show Keys, copy the private key. Again, if you're using Anvil, use the private keys there. If we keys, copy the private key. Again, if you're using Anvil, use the private key we want to do. And if we're in our command here, let's hit clear and we do forge create dash dash help. We can see a ton of different options for deploying our contract. Click show keys, copy the private key. Again, if you're using Anvil, use the private keys there. If we do forge create simple storage, which is the name of our contract, it'll compile. And then it'll throw an error actually, or it might actually work. But because I'm working with this RPC server, but this RPC server is different from the one that Forge actually defaults to. So instead, what I can do is forge create simple storage dash dash RPC dash URL, copy this, paste it in here. It might be upset with the uppercase. So let's just make that lowercase and I'll hit enter and this won't work either. Well, of course, we forgot to add a private key. So if I hit up, I can hit dash dash interactive as well. And now it'll prompt me for a private key. Now, and a really important note that I want to tell you, never use a real private key in your VS Code if you're using an application that potentially will send your information. A much better option is to use your own terminal as opposed to something like VS Code, which might send data, or Gitpod. Since we are just developing and we're just practicing, it's fine to paste our private keys here because this is a private key that's not going to have any real money, right? It's a fake private key. So for now, we can go ahead, we can go back to our Ganache or back to our Anvil, hit show keys, copy this private key, paste it in here. It won't show up if you hit paste, but I'll hit enter and we'll go ahead and see information about our transaction. Now, if you're working with Ganache, we can now hit done here. We go to blocks. We see we created a new block. We go to transactions. We can see that we sent a transaction and we created a contract. Transaction here, information about our transaction. Now, if you're working with Ganache, go ahead and see information about our transaction. Now, if you're working with Ganache, we can now hit done here. We go to blocks. We see we created a new block. We go to transactions. We can see that we sent a transaction and we created a contract. And then you can see logs about working with this as well. Fantastic. If you're working with Anvil and you send a transaction, you're not going to see any of those details. For those of you who want to continue to see these blocks and these transactions and want to keep working with Ganache, feel free to do so. Moving forward, we're going to work with Anvil. So I'm actually going to close Ganache now. I'm going to hit clear in the terminal and I'm going to run Anvil here. And what I'm going to do is I'm going to create a new terminal by hitting the plus button here. And we're going to run that command again, but we're going to run it with a private key from Anvil. So if we go to here, we can do forge, create. This time we don't have to put an RPC because Forge defaults to the Anvil one, but I can say simple storage /interactive. It'll do enter the private key. I will paste it and we'll go ahead and deploy. Go to Anvil. We don't get any logs like this, but we can see we went ahead and actually deployed it to our Anvil blockchain. Awesome work. Another way we can do this forge create is by running forge create simple storage. If we wanted to be incredibly explicit, we would do --rpc -url, copy this, http:// paste it in there, --private key, and back in Anvil, copy the private key, paste it in like this, and we would get the same thing. Now, here's what I'm going to tell you, and this is incredibly important. Pasting in your private key like this is no bueno. Very bad. We pretty much never want to have our private key in plain text, especially our production or our private keys with actual money. Putting this private key in plain text is not a big deal because this is a fake dummy one. It's also bad to have our private keys in our shell or bash history. If I hit up once on my terminal, I can see the private key in here, which is why the interactive is a little bit better because it at least obfuscates the private key. To remove your private key from your history in bash, you can do history-c. Now, if I hit up, I can't see any commands. And if I do history, I can see my entire history, which is just the history keyword. Now, if I type clear, I'll do history. Now I see history, clear, history. Great. And we don't have the private key in our command history anymore. We will learn more about, great. In bash, you can do history-c. Now, if I hit up, I can't see any commands. And if I do history, I can see my entire history, which is just the history keyword. Now, if I type clear, I'll do history. Now I see history, clear, history. Great. And we don't have the private key in our command history anymore. We will learn more about proper private key safety in the future, but I want you to do something for me right now. In a new file, I want you to right click and I want you to write promise.md. We're going to hide the terminal. And in here, we're going to say, I promise to never use my private key associated with real money in plain text. In fact, take this and tweet this. I promise to never use my private key associated with real money in plain text. And I can't spell, and that's fine. And then if you want to @ me, or you want to @ Cyphernautics, or whatever, go ahead and send that. We are going to have more of these promises that you're going to do, but this is the first one that I need you to understand. Right now it's cool because these are dummy keys, but in the future, it will definitely not be cool. And I'm stressing this because I've seen a lot of multi-million-dollar companies not follow this and get their private keys hacked. Great. Now, of course, though, the basic way to deploy to any blockchain would be forge, create the name of your contract, add the RPC URL, and then add your private key. We're going to learn how to get RPC URLs for free using Alchemy for any blockchain that we want. And like I said, more safe private key methodologies in the future. But now you've just learned how to deploy your contracts to any chain from the command line. This is great. All right, great. So now we've learned how to actually deploy a contract to any blockchain that we want using the command line. But now I'm going to teach you the second way we're going to deploy our contracts. And this is the way we're actually going to do it for the rest of the course. When we're deploying our code, we want to make sure we have a continuous, reproducible way to deploy our smart contracts. And when we test our code in the future, we want the tests to test the deployment processes as well as the code. So instead of just doing the command line, we're actually going to write a script for us to deploy our code. And because Foundry has everything written in Solidity, this script that we're going to write to deploy our code is also going to be written in Solidity. And this is where Solidity as a contract language versus Solidity as a scripting language is a little bit different. Foundry has a whole bunch of built-in stuff to give our Solidity even more functionality outside of just smart contracts. And you'll learn about how later in the course. But for now, we're going to learn how to create a script to deploy our simple storage contract. And the way we create a script to do it is first, we come to our script folder, we'll right click, new file, we'll create deploy simple storage.s.sol. This .s.sol is just a Foundry convention. Most of the time, scripts have a .s.sol instead of just being .sol. And in here, we're actually going to write a contract in Solidity to deploy our smart contract, which sounds a little bit weird, but don't worry too much about that. This deploy script is going to be written in Solidity, but it shouldn't be considered a contract that we actually ever want to deploy. It's just for deploying our code, but it is written in Solidity. So since it's written in Solidity, we'll do the same thing as usual, SPDX license identifier, MIT. And if you're using GitHub Copilot, it might even auto suggest like this. And I'm just going to go ahead and hit tab. I'll do Pragma Solidity 0.8 8.18. And then I'll create contract, deploy simple storage like so. And I'll hit save. If you go to the Foundry docs, we can actually scroll down to this Solidity scripting section in the tutorials. And you can learn how to actually write scripts and work with scripts. The first thing that we need to do in order to tell that Foundry that this is a script is we need to actually import some additional code. Now, one of the things that we saw in here was this lib folder. And this lib folder actually starts with another folder called Forge STD. This Forge STD stands for Forge Standard Library. In here, there's a ton of helpful tools and scripts for working with Foundry. And to tell Foundry that this contract deploy simple storage is actually a script, we need to import from Forge STD. So we can do import forge -std /script.sol. And we'll have our contract deploy simple storage inherit all the functionality of this script by saying is script. And I know we learned about inheritance before, so you should know what that means, is script. And then additionally, our deploy simple storage is going to need to know about our simple storage contract. So we'll go ahead and import that. Import, we'll go down a directory since we're in the script folder and we need to go to the src folder. These two dots is how you go down a directory. We'll do /src. VS Code even might help prompt you here. Dash, and it again auto prompted for me, and I hit tab, and now we've imported simple storage. Now, since we know that this is the noob way to do imports, we're going to do the cool way by using named imports instead of nameless imports. Okay, great. Great. Now, inside every deploy or script contract, we need our main function, which is going to be called run. And this is going to be the command that gets called when we go to deploy our contract. So we'll create a function called run. We'll make it external, and we can have it return a simple storage contract. And in here, we're going to use a new keyword that we haven't used before. We're going to say vm.start broadcast. VM is a special keyword in the Forge standard library. The VM keyword is a special keyword that we can only use in Foundry. It's related to something called cheat codes. We're not going to go over that too deep right now. You can see a whole list of Foundry cheat codes in the documentation and Forge standard library references, which have even more cheat codes as well. This VM stuff is only going to work in Foundry. If you actually were to try to deploy this in Remix or some other framework, it wouldn't work. These VM cheat codes only work in Foundry. It's not valid in regular Solidity, but if we're inheriting Forge STD code, this VM keyword exists. If you're using the Hardhat Solidity extension, we can actually control or command click into VM, and we can actually see where it's defined. But if that's confusing, ignore that for now. This vm.start broadcast says, hey, everything after this line inside of this function, you should actually send to the RPC. And then when we're done broadcasting, we're going to do VM. Stop broadcast. So everything inside of these is what we actually want to send and deploy. The reason we have this is because maybe we have some stuff like we want to set some boilerplate code before we actually send transactions, and we don't want to spend any gas to like set starting value to 1, right? So any transaction that we want to actually send, we need to put in between these vm.start broadcast and vm.stop broadcast. And for us to deploy our simple storage contract, we just do simple storage, lowercase simple storage, right? These are different. Simple storage, the variable, simple storage, the contract. Equals new simple storage, like this. And remember, what does this new keyword do? Well, the new keyword creates a new contract in Solidity. It's also going to create a new contract in between our VM VM.startBroadcast. This, being in between these VM.startBroadcast, is going to send a transaction to create a new simple storage contract. If this is a little bit confusing for you right now, that's okay. It's going to make more sense as we go on later in the course. But for now, just do this and follow along with me. And then, of course, we can say return simple storage. Okay, great. Now, if we pull our terminal back up, we can see we have Anvil running right now. We can actually kill it with Control C. We'll clear to the top. And what we can do now is run forge script deploy simple storage.s.sol, hit enter. And look, oops, looks like I got some different Solidity versions. So let's change this to a caret in here. And let's change this to a caret in here. This being an 18 so that they're both on the same version. Let's type clear, close these. Or minimize these out. We'll hit up twice and we'll run this again. And now what you'll see is it's compiling. It compiles both the script to deploy and our simple storage contract using 0.8.19 because we did the caret. Compiler successful, script successful, tells us the gas, and then we went ahead. We returned our simple storage contract, which was deployed here. Now you might be asking, wait, Patrick, we don't have Anvil running. We don't have a local blockchain running. Where did this deploy to? Well, in Foundry, if you don't specify an RPC URL, it'll just automatically deploy your contract or run your script on a temporary Anvil chain. So once I ran forge script, it saw there was no RPC URL, so it spun up a temporary Anvil blockchain, deployed our simple storage, and then tore it back down at the end. You can see at the bottom, if you wish to simulate on-chain transaction, pass an RPC URL. So if we do clear, we run Anvil, and then create a new terminal. We could run forge script deploy simple storage.s.sol, and I'm hitting tab to autocomplete that. --RPC URL, go back to Anvil, copy this, go back to bash, http ... We actually almost deployed this to the blockchain. We actually did a simulation of deploying to our Anvil chain here. It gives us one more piece of information to broadcast these transactions, add -- broadcast and wallet configurations to the previous command. And now we get a new folder, which gives us information about our previous deployments in case we forget. For example, if we deploy a contract, we can flip back here and see where we actually deployed code. So let's pull up our terminal once more and actually deploy this to the blockchain. So we'll hit clear. I'll hit up. We have our RPC URL. So now let's do -- broadcast, and we'll do -- private key, and we'll grab a private key from Anvil and paste that in here and hit enter. Boom. And we see at the bottom, on-chain execution complete and successful. And we see we get some transactions here. We waited for receipts, etc. So fantastic. So we learn, we get some transactions here. We win execution complete and successful. Boom. Private key from Anvil and paste that in. In here and hit enter. Boom. And we see at the bottom, on-chain execution complete and successful. And we see we get some transactions here. We waited for receipts, etc. So fantastic. So we learned how to actually deploy our smart contracts through the scripting command now. Awesome job. Now let's learn a little bit more about what. Actually just happened, right? Because right now, sending transactions is still kind of this magic thing, right? So let's hide our terminal and let's go up to our Explorer. Let's pull this out a little bit and let's go into here. Now, what's important to note is that there's actually a couple different folders in here. Dry run is the folder whenever we don't have a blockchain running. Otherwise, this gets separated by chain ID, and we'll talk about this a little bit later. But if we go into one of these, either dry run or even just run latest, we'll see details about the transaction. We'll see a hash, transaction type, contract name, address, blah, blah, blah. This right here, this transaction section is actually what is getting sent on the chain. When we do forge script or forge create, this is the transaction that we send to that RPC URL, right? This is the API data. If you're familiar with HTTPS post, this is the transaction section is actually what is getting sent on the chain. When we do forge script or forge create, this is the transaction that we send to that RPC URL, right? This is the API data. If you're familiar with HTTPS posts, this is the data that we actually send. We send the type, which for now, just everything is type 2 because we're in the merge. Don't worry about type 1 for now. We have a from, which is, of course, the from address that we want to have. We have a gas here, and this is the hex value of gas. Now, if we pull our terminal back up, we'll clear this out. I'm about to show you an amazing trick that's going to make your life a lot easier down the line. Cast actually can convert between hex and numbers really easily, and Cast comes built in with Foundry. We do cast dash dash to base, paste our hex in here and write DEC for decimal. It'll convert this hex value to its decimal value. 0x714. C2, whatever, is just this number. And I use this cast to base all the time. You can put some value in here and then what you want to convert it to. And it's a very easy way to see what some value is. There's some other stuff in cast as well. If you do cast dash dash help, there's some other ways to convert different units to each other, like from way, bytes 32, and some other stuff. But to base is going to be one that we're going to use a lot. So we have the gas, we have the value with the transaction. Yes, since deploying a contract is just a transaction, we can add a value to it if we want. In our deploy script, right in here, we would just do some brackets. We would say like value and like 1 ether if we wanted to deploy this with 1 ether. We can't send a value here because in Solidity, you can't set the option value if the constructor is not payable. We'd have to make the constructor payable, but we could send value just like any other transaction. There's this huge data piece here. This is actually the contract deployment code and the contract code in here. We have the nonce, which is going to be that number that's only used once. And then don't worry about access list for now. But this is all the transaction information. And then of course we have our RPC. Now what's not stored in here is a couple other pieces of the transaction. Now additionally, there are these V, R, and S values that account for the transaction signature. It's not getting saved here because it's technically part of this from anyways, they're public values. And these R, S, and V allow our private key to sign the transaction. So what's really happening when we send this, the reason we need our private key is we need the private key to actually sign the transaction that we built. And that's happening a little bit under the hood. So whenever we send a transaction, there is a signature happening. We are signing a transaction and then we are sending it. And that's important for later in the course. They don't save it here, but signing the transaction does happen. happening a little bit under the hood. So whenever we're not getting saved here because it's technically part of this from anyways, and the contract code in here, we have the nonce, which is going to be that number that's only used once. And then don't worry about access list for now. But this is all the transaction information. And then of course we have our RPC. Now what's not stored in here is a couple other pieces of the transaction. Now additionally, there are these V, R, and S values that account for the transaction signature. It's not getting saved here because it's technically part of this from anyways, they're public values. And these R, S, and V allow our private key to sign the transaction. So what's really happening when we send this, the reason we need our private key is we need the private key to actually sign the transaction that we built. And that's happening a little bit under the hood. So whenever we send a transaction, there is a signature happening. We are signing a transaction and then we are sending it. And that's important for later in the course. They don't save it here, but signing the transaction does happen. When you sign a transaction, it's very similar to doing that hex thing we showed you way at the beginning of the course with the blockchain. Only the private key can sign the transaction. This is how, when we send our data to a node, it knows that it's able to execute it because it's signed by our private key. I'm not going to go too deep into that right now. Now, this nonce piece is a little bit important. Every single wallet has a counter of transactions, which is basically the nonce. Whenever you send a transaction, you give it a nonce, or this value, this number only used once, to basically count your transactions. This is really good because if you want to replay transactions, you would just send the same transaction data with the same nonce. For example, if we have a transaction that didn't go through, you'll see that this is in this run latest for the dry. If we run this again, if we hit up, you'll see that if we run our transaction again with our Anvil deployed here, we'll actually deploy another transaction. If we go back to our broadcast folder, we see there's actually 2 runs and a new run latest. If we go to our run latest now, you'll see that the latest run now has 0x1. So this increments every single time we send a transaction. Your nonce increments every time you send a transaction. And again, contract deployments are transactions. Now, we went over a lot of stuff in here, but the most important takeaway I want you to have from this is anytime you change state on the blockchain, it does it in a transaction. And the differentiator is going to be whatever in this data field. This data field contains the opcodes to tell the blockchain, hey, I'd like to create a new contract. We're not really going to go too deep into what these opcodes are, or this EVM bytecode. We'll briefly talk about opcodes later in this course, but if you want to really learn about opcodes and assembly, we have another course on security coming out that will go over that. But this is the most important thing to take away. When we're in Remix and we're sending transactions with these buttons, we're doing the exact same thing. We're populating the data field of a transaction, but instead of the data being associated with creating a contract, the data is associated with sending a transaction.